Welcome to The Explainer. Today we are diving into a core programming concept that's, well, both incredibly elegant and just a little bit mind-bending. We're talking about recursion.
So let's just jump right in with a picture. If you've ever seen an image that has a smaller version of itself inside of it, which then has an even smaller version of itself inside of that, well, you've already seen recursion in action. It's this idea of a pattern that repeats itself just on a smaller scale. And really, that self-similar pattern, that's the whole key. In the world of programming, it's a way of solving a big problem by breaking it down into smaller and smaller versions of the exact same problem. Okay, I know what you're thinking. That sounds like a riddle, right? A function that calls itself? Shouldn't that just get stuck in a loop and run forever? So what's the trick? How does it know when to stop? To figure that out, we've got to peek under the hood and see how the computer keeps track of all this. To see how the computer avoids getting trapped in that infinite loop, we're going to use a really great analogy. The way it manages all these self-calls is a lot like a stack of trays in a cafeteria. Just imagine, every single time a function is called, it's like someone puts a new tray on top of a stack. Then, if that function calls another function, a new tray gets placed right on top of it. So you see the process, right? We're adding trays, then we're taking them away. But the order that we take them away in, that is the most important part. And it all follows one simple, very strict rule. And here it is. This is the key. The computer always works on the most recent task first. Just like in that cafeteria, you can't get to the bottom tray until you take the one on top off first. This whole concept is known as last in, first out, or LIFO for short. Okay, now that we've got this mental picture of a stack of trays, let's actually apply it to a classic programming problem where recursion really gets to show off, calculating a factorial. Now, sure, you could just use a simple loop, right? Multiply 1 times 2, then times 3, and so on all the way up to 5. But let's try to think about this recursively. You see that pattern? A recursive function breaks the problem down. It basically says, hey, I don't know the answer for 5 yet, but if you could just get me the answer for 4, I can figure out the rest. And each one of these calls adds a new tray to our stack. Fact of 5 calls fact of 4, which calls fact of 3, and on it goes. But it can't go on forever, right? It needs a stop sign. In recursion, we call that the base case. It's a simple condition that finally stops the chain of calls. For factorials, that base case is 0, because the factorial of 0 is just 1. So once fact of 0 returns the number 1, its tray gets taken off the top of the stack. That result, 1, gets passed back to fact of 1, which can now finish its job. Then its tray is removed. And this just keeps happening, unwinding all the way back up the stack until we get our final answer, 120. You have to admit, that's a pretty clean way to solve the problem, isn't it? It's really elegant. But, and there's always a but, that elegance can come with a pretty big trade-off. And what's so cool about this slide is you can see it side by side. I mean, the loop on the left works just fine, but look at the recursive solution on the right. It almost perfectly mirrors the mathematical definition. It's often way more readable and just concise. But here's the catch. The biggest issue is performance. Remember all those trays? Every single one of them uses up a little bit of memory. So if you make too many recursive calls, like trying to find the factorial of some huge number, you can literally run out of space, and that causes something called a stack overflow error, which will crash your program flat. And you know, that memory problem isn't the only risk. Some problems, if you try to solve them with a simple recursive approach, become ridiculously inefficient. And the classic example of this is calculating the Fibonacci sequence. So let's say you want to calculate the 6th number in the sequence. A simple recursive function just ends up doing a ton of wasted work. It calculates the same values over and over and over again in completely different parts of the process. It's like asking it to calculate fib of 2, and then 10 minutes later, asking it to calculate fib of 2 all over again from scratch. It's elegant, sure, but the gears are just grinding for no reason, making it way slower than a simple loop would be. Okay, so if loops are usually faster and safer, why do programmers even bother with recursion? Is there any point to it? Oh, absolutely. It all just comes down to using the right tool for the right job. You wouldn't use a hammer to saw a piece of wood. Recursion isn't for everything. It really shines when the problem you're trying to solve is itself naturally recursive. So here's the big takeaway. You should reach for recursion when your data is recursive.
Think about your computer's file system, right? You have folders that contain files, and also other folders, which themselves can contain more files and folders. For these kinds of nested, self-similar problems, the clarity of a recursive solution is often worth it, making really complex logic much easier to write and, more importantly, to understand. Ultimately, recursion is more than just a technique. It's a really powerful way of thinking. It's about solving a huge problem by just assuming you can already solve a slightly smaller version of it. It teaches you to break down these massive challenges into tiny, manageable pieces, and to find that simple, elegant pattern that's hiding inside all the complexity. And honestly, that's a lesson that goes way beyond just writing code.